Okay, so now that we've covered exponential functions and we've done some problems, let's now talk about logarithmic functions. And so what is a logarithmic function? And the concept of a logarithmic function is directly related to the exponential because of the following. First off, if we remember the exponential function, which is y equals b elevated to the x, where b is a number that's larger than 0 and different to 1, if we were to graph that function, assuming a number from 0 to 1, we would get something like this. And if we also remember this function, or the exponential function, is a one-to-one function. Okay, so if it's a one-to-one function, that means that I can find the inverse of that. And so this is the exponential function that we're drawing here. Okay, and so if we have y equals b to the x, and this is a one-to-one function, then the inverse of it would be x equals b to the y. Using the same procedure that we used previously for the inverse, we substitute x for y and y for x. And so the way we enunciate this or say this is that y is the exponent of base b that produces x. So if originally I have y equals b to the x, okay, that means that I have a number that's elevated to a power, then the inverse of that would be the answer to what power would I need to elevate the base b to get x. Okay, so I'm sorry, what exponent of the base b would produce x? Sorry about that. Now this is this is kind of like a word tangle. So let's try to explain this with some numbers. Let's assume that I have 2 elevated to the 3. Okay, what does that mean? This means that 2 elevated to the 3 is 2 times 2 times 2, and this gives me what? 2 times 2 is 4, times 2 is 8. This is the exponential, okay? This is this one that we've got here, okay? Now, what if I told you that I have the number 8, and I want to know what is the number that I would need to elevate 2 to get x, meaning that I want to know what is the value of x. That's the definition of the inverse. So if 2 to the 3 is 8, then what is the value that I would need to elevate 2 to get 8? Well, the response here is that the value would be 3, okay, which is the one I used here. Okay, and so that's what this phrase here is trying to tell us. So what is the inverse of the exponential function? So y is the exponent of the base b that produces x. So somebody said that that's going to be kind of confusing. It's confusing. It might still be confusing, but somebody said that that's going to be a bit confusing. Let's use another name to represent this. And so instead of using the word exponent, somebody thought about using the word logarithm. And so the rephrase is that y is the logarithm of the base b that produces x. So that's where the concept of a logarithm comes about. So a logarithm is basically the mathematical operation where we are identifying an exponent that I would need to elevate a base b that would give me a specific number. And it's the inverse operation of the exponential. So a logarithmic function with base b, and again, same restrictions. B has to be larger than 0 and different than 1 is defined as log b of x, or the base logarithm of x equals y. And this only happens if x equals b to the y. So what does this mean? When we're looking at a logarithm, remember this example is, what is the number that I would need to elevate b to get y? And that is, I'm sorry, what is let me rephrase that. I'm sorry, I said that wrong. What is the number b that I would need to elevate? What is the number that I would need to elevate b to get x? And that would be y. Okay, so again, in this example, 2 to the 3 is 8. So I elevate 2 to the 3, I get 8. What number would I need to elevate 2 to get 8? That would be 3, and that's the logarithmic function, or the logarithmic mathematical function. Okay. And so logarithms also have laws, and these are directly derived from the laws of the exponents. So again, for any base b larger than 0 and different than 1, and assuming that we have two numbers, the log base of b of m multiplied by n. So meaning if I have a logarithm of two values that are multiplying, that can be separated into the logarithm of m plus the logarithm of n. So the multiplication gives me an addition, because again, it's the inverse as the exponent. So for example, if I have log base 2 of 3 multiplied by 2, then this would be the same as having log base 2 of 3 plus log base 2 of 2. Something similar happens with the division. So if I have a division, the division is going to generate a subtraction. And again, that's a relationship with the exponent. So if, for example, I were to have log base 2 of 3 divided by 2, then it would be log base 2 of 3 minus log base 2 of 2. So it's a division. If I have a log of a number and that's elevated to a power, then what happens here is that this power that's elevated to comes back multiplying here. And this also comes from the laws of the exponents and the inverse. So for example, if I have the log, if I have log base 2 of 3 elevated to the 5, then what happens here is that this 5 is going to come over here multiplying. This is equivalent to 5 log, log base 2 of 3. And again, these I imagine aren't new to you guys. Again, in previously in any math course, you might have seen these laws. And again, they're common laws that are derived from the laws of the exponentials. A few rules that are also apply here. So the log b of 1 is equal to 0. And again, this is because b elevated to the 0 equals 1. Okay, so always the logarithm of 1 is equal to 0. And also the logarithm b of b is always 1, and this is because b elevated to the 1 is equal to b. Okay, and so we're going to be using these laws and applying them to operations we're going to be doing. Okay, and so the graph of a logarithmic function also is a very particular model. And so what we see here in these two examples, the blue function, the blue graph, I'm sorry, is y equals b to the x. It's the exponential, okay? And what happens with the logarithm? The logarithm is going to be a reflection along the origin of the exponential function. So what we're going to see is that the logarithm starts off at a very large number and then starts growing. It crosses in 1 and then starts growing, but at a slower rate. And the same as in the exponential function, the asymptote was the x-axis. Now the asymptote is going to be the y-axis. It's never going to cross the y-axis. And so if we have the same function here, but for this one, for example, remember that b is larger than 1. Yeah, that's important. B is larger than 1. So for example, I don't know, here b would be equal to 3. In both cases, the exponential and the logarithm, it's larger than 1. But then if we have b from 0 to 1, remember that there's a reflection in the exponential one, so it decays. For the logarithm, we're also going to see here a reflection, and it's going to start off at a very large number, then it's going to decay. It's also going to cross here in x equals 1. The same as with the original exponential, that the x was a horizontal asymptote. Now we're going to have a vertical asymptote in y, and it's going to start decaying slower once it goes down, and it decreases. That's also important here. In the case where b is larger than 1, then the function is increasing. With b between 0 and 1, the function is decreasing. And just to be clear, here, for example, would be the case where b equals 1/3, for example. Just as an example. So here b is larger than 1. Here b is between 0 and 1. We see these two behaviors. Okay, and so logarithms also have properties similar to the exponential function. The domain, remember that when we're talking about inverse functions, the domain and the range get switched. So for an exponential function, the domain was from -infinite to infinite, and the range was from 0 to infinite. For the logarithm, it's going to be the other way around. The domain is going to be from 0 to infinite, and the range is going to be from -infinite to infinite. We're going to have an x-intercept in 1, 0, but we are going to have no y-intercepts. Okay, that's same as the exponential. In the exponential, we had a y-intercept that was 0, 1, and we didn't have x-intercepts. For the logarithm, it's going to be the other way around. We have an x-intercept in 1, 0, and we have no y-intercepts. Let me clear this. And this is what we were talking about. It's going to be increasing for b larger than 1 and decreasing for b from 0 to 1. And this is what we were talking about in the previous slide. So for b larger than 1, it's going to increase. For b larger than 1, it's going to be increasing. For b between 0 and 1, it's going to be decreasing. The y-axis is going to be the vertical asymptote. Okay, So we're going to notice here that the y-axis now is going to be an asymptote, okay, meaning it's never going to cross the y-axis. It's going to get close to the y-axis, but it's never going to cross it. So it's going to be a vertical asymptote. It's going to be continuous from 0 to infinite. Okay, and the function again is also 1 to 1. Okay, so if we look at the function here and we apply the horizontal line test, we see that it is 1 to 1. And that's important because the logarithm is the inverse of the exponential, and the exponential is the inverse of the logarithm. So both of them are 1 to 1, and the inverse of each can be calculated. And this is also congruent with the properties of a 1 to 1 function. The inverse of a function should also be 1 to 1. So now if we apply the natural logarithm, or I'm sorry, if we use B, or rather we choose as B the value of E, or Euler's number, the one we just mentioned. So if that would be the base for our logarithm, then it's a special function that's called the natural logarithm. You've seen that instead of using log, we use ln. When we use ln, this is the same as saying, it would be equivalent to saying log base E. This is equivalent to natural logarithm. And the natural logarithm function is going to have the same graph as the logarithm function. The only thing is that we're going to have a couple of interesting reference points here. We're still going to be crossing here in 1, 0. But in this case, the behavior of the function of the base is going to be defined by E, or by Euler's number. And so what are applications of logarithms or logarithmic functions? Well, for example, the Richter scale is an application of a logarithmic function. Okay, so in the case of a logarithmic function, in the case of the Richter scale, if you remember a little bit about what the Richter scale means, if you have a earthquake of magnitude 4, and then you have an earthquake of magnitude 8, the magnitude of the 8 earthquake isn't the double of the magnitude of the 4 earthquake. So a 4 earthquake can be dangerous, but an 8 earthquake can be catastrophic. And so the Richter scale is an example of a logarithmic scale. And basically a logarithmic scale is a scale in which if we were to look at the number line, a normal number line, if we were here in 0, the spaces between the intervals are the same. Okay. In a logarithmic scale, the spaces between the intervals are not necessarily the same. Okay. The spaces between the intervals are going to be different. And so the Richter scale is an example of that. Again, the magnitude between 0 and 1 and 1 and 2 are small, but the magnitude between 2 and 4 is larger. And the magnitude between 4 and 6 is larger, regardless of if in units the separation is 2, the separation in the scale is larger. So the Richter scale is an application of that. And also, for example, the pH solutions used in chemistry to represent hydrogen concentration in any sort of solution, like, for example, human blood. And so these are some examples of logarithmic models or scales. Sound also, decibels are also measured in or power that's used sometimes in sound applications. So when you have your sound system and the sound system is a certain amount of decibels, that's also given in a logarithmic scale. So these are just some examples of how logarithms are used or can be applied. Okay, so now we've covered logarithmic functions, and the next thing we're going to do is that we're going to see a few examples. We're going to be solving some problems.